Hello. All right, we have lots to do today. If you have any questions on homework, if you could just reserve those until maybe the end of class, because I think after today I might resolve some issues that you may have on the homework. We are going to try and get out of 8.1 today. It's going to be a task. There's a lot in 8.1. There's little subtle things. I want to show you quite a few examples. So we'll do our best to get out of 8.1. We're supposed to be, today, we're supposed to be starting 8.2. So, you know, we'll see how things go. All right, so we left off talking about sequences, right? And the last thing that we discussed was the Squeeze Theorem. And then right after the Squeeze Theorem, I gave you this theorem that says if the absolute value of your sequence goes to 0, then the sequence without the absolute value must also go to 0. And I gave you an example here of that. And then after that, I showed you an example where you had to be careful because we had a sequence that alternated from -1 to 1, -1 to 1, and then we took the absolute value, which just gave you 1, 1, 1, 1, 1. We said, well, that converges to 1. So does that theorem tell us that this must converge to 1? And we said no, because the theorem said the absolute value of the sequence had to converge to 0 for the theorem to work. So just something to be careful with. That's where we left off. And I'm going to kind of pick up there today. So our first note is another theorem. And it says that if the limit as x approaches infinity of f of x equals L, and f of n equals a sub n, then the conclusion of this theorem is that a sub n, what's that little arrow mean for us now? Approaches or converges to L, right? This notation is the same as saying limit n goes to infinity of a sub n equals L. So anytime we use that little arrow, that's what this means. So let me try and explain what's happening here. The theorem says that if you are looking back in like a Cal 1 setting where you had some function of x is allowed to be a real number. Remember, sequences are functions, but we restrict their domains to integers, right? Functions of x, we usually let x be any number, so it can take on you know, all sorts of values, decimal values like 0.2, we can plug in pi. So this is saying if you're looking at a traditional Cal 1 function and it has a limit as x goes to infinity, and then you come in and you define your sequence to be that function but restricted to just the integers, then if this goes to L, then the sequence must go to L. It's much easier to see with the picture. So here's the picture. Let's say you have a function. Now the one I have here, I know it's difficult to see this, but it's n squared over 1 plus n squared. That's our sequence. So what we do is we say, what does that sequence do? N squared over 1 plus n squared. Well, instead of looking at it as n squared over 1 plus n squared, let's look at it as x squared over 1 plus x squared. So back like a function in Cal 1. A function is defined, it's nice and continuous and smooth, and we can kind of see here that this function appears to be approaching a limit as we go to infinity. It appears to be approaching 1, right? So whatever that function does, if we then come in and say, okay, let's just define our sequence as that function, but only at the integers, then we're talking about only those dots, right? And that red thing isn't there anymore. So whatever the function does, the sequence must also follow it. Does that make sense? That's all the theorem says. And this is vital because what we're going to do is we're going to try and figure out where certain sequences are going. We're going to have difficulty doing it. So we're going to go back and look at the function, the Cal 1 function, and use things like L'Hopital's rule and different techniques of figuring out what happens as x goes to infinity, whatever happens there must happen for the sequence. But the theorem is what guarantees us that will happen. Okay? Understand visually? All right, let me turn my phone off. Okay, so that's our first note. Let me try and give you an example of this. An example of this would be something like, where's the one I want to do? I have these circled, but where did I put it? There we go. Find the limit as n goes to infinity of 1 plus 5 over n to the n. So what we need to realize here is that the sequence we're talking about, a sub n, is 1 plus 5 over n to the n, right? That's our sequence. Now, I did not tell you where we would start n, so since I don't tell you where we start, what do you assume it starts with? 1, okay. So, like if I wanted to see the first term of this sequence, I would plug in 1, right? I plug in 2, and then 3, and then 4, and then keep going, right? And I want to know what happens as n goes to infinity. So let's just look at the behavior here. What does 5 over n go to? It goes to 0, right? You have a fixed number over something that's huge, that goes to 0. Now, it's always going to be something, right? But it's going to be approaching 0. 1 plus something approaching 0 is going to be very, very close to 1, right? So it looks like the base of this expression, right? This base, I'm doing it in red because I'm saying that's what it's approaching, appears to be approaching 1. Now, the exponent then comes in and raises it to a power, right? So the power, though, is getting bigger and bigger and bigger, right? Because n is going to infinity. So what we get is something that looks like 1 to the infinity. And in Calculus 1, this is what we refer to as an indeterminate form, meaning that if something is trying to be 1, right? If I say, take the number 1 and raise it to any power, your answer should be what? 1. But if we raise things to powers, they normally get bigger and bigger and bigger, don't they? And since this number down here in the base is not exactly 1, it's a little bigger than 1, then when I start to raise it to huge powers, it does want to get bigger. So there's this battle going on. The exponent wants to make this thing blow up. The base wants to become 1. So who wins the battle? And there's really no easy way to determine it unless we use some stuff from Cal 1. So what I'm going to do first is I'm going to look at, let's investigate the function f of x equals 1 plus 5 over x to the x. So what I've done is I've transformed this sequence, which is only defined on integers, to a function which is defined on all real numbers. Now you'll see the value of that in a second. If I now come in here and try and evaluate this limit as x approaches infinity of 1 plus 5 over x to the x, and I think next to this over here, I'll put x is an element of the real numbers. In other words, x is a real number, just to make sure you understand that we're switching from the sequence to the function. Then if I want to figure out what happens to this, whatever happens to this, our sequence should do the same thing, all right? So we have this indeterminate form, 1 to the infinity. Anytime in Cal 1 we had that sort of form, what we normally did was we called this limit something like y. So I'd like to know what y is. So we make an equation out of this. And the reason we did it in Cal 1, in fact, I did this in my last Cal 1 class yesterday, is because if you make an equation, then you can do something to both sides. So what I'm going to do is I'm going to take the natural log on both sides, and you'll see what happens. We are also going to utilize a property of limits that says if I take the natural log on the left side, I get natural log y. If I take the natural log on the right side, I can pass the natural log through the limit. In other words, the limit can stay outside. And it comes back from Cal 1. There's these things called the limit laws. So I'm going to put a natural log right here, and then I'm taking the natural log of 1 plus 5 over x to the x, and I'm out of room. So next page. Okay. Now, why is it that we introduced the natural log? I mean, that's right, because there's a property of natural logs that says if you have natural log of x to the n, this is n natural log x. In other words, that power here can drop out in front. Okay, so what I'm going to do is I'm going to take this x and I'm going to drop it out in front of this natural log. So natural log y, notice I'm keeping the equation, is limit x goes to infinity of x times now natural log of 1 plus 5 over x. The reason I'm showing you this example is not only because I want you to see how we convert a sequence to a function, like a function of a real variable, but because what's required here is drawing back from Cal 1. And there's a lot of stuff like that in this chapter where you're going to have to go back to stuff from Calculus 1 and pull from that. So just be aware of that. I don't want you to be too surprised when it starts to happen. Okay, so now let's just take a look real quick what happens as x goes to infinity. As x goes to infinity, this one right here goes to infinity, right? Then times, now let's look at this one. We have 5 over something that gets big goes to 0. 1 plus something that gets close to 0 is close to 1. The natural log of 1 is 0. So what's happening is this is getting very close. This whole thing right here is getting very close to 0. Not ever getting to 0, but very close to it. So in the limit, that's approaching 0. And whenever we have this in Calculus 1, this is again an indeterminate form. You have a number that's getting huge times a number that's getting small, right? And for that, you don't know what happens. So you have to continue to do something. And the standard technique that we use when we have infinity times 0 is we take one of these and we drop it to the denominator as 1 over it. So let me just write down what I'm saying there. Natural log y is limit x goes to infinity of natural log 1 plus 5 over x. What I'm choosing to do here is drop this x that was out in front down to the denominator. But when I move it to the denominator, it can't just be an x in the denominator. It has to be 1 over x, right? Like, have I changed the problem at all here? 1 over x really would flip back up and the x would be here, wouldn't it? So I've just written it this way, and I've written it this way because now, let's just check again to see real quick what happens. We know when I plug in a huge number here, this goes to 0, and then that's 1. So natural log of 1 we said was 0. So the top is going towards 0, and the bottom is headed towards where now? 1 over something big is going to go to 0. So we get 0 over 0. And this is what makes us happy, because whenever we have 0 over 0 or infinity over infinity, either way, you can apply L'Hopital's rule. Okay? Did we talk about L'Hopital's rule last class? No? I didn't mention it at all? 2 or 3 classes ago? Okay. So L'Hopital's rule says that if you have this ratio of 0 over 0 or infinity over infinity, whatever this limit is equivalent to the same limit, but you take the derivative of the top and the derivative of the bottom separately. And then look at that new expression and find its limit. Whatever that limit is equal to this limit. So you can go look up L'Hopital if you need to. In fact, if you get on my YouTube channel and you look at my playlist for Cal 1, I just covered it the last 2 classes in Cal 1, so you could go back and review if you wanted. I did a bunch of examples in there. I go through each case. You know, what happens if you have, 0 times infinity, if you have 1 to the infinity, if you have, infinity to the 0, all these different scenarios that you run into. So, okay, I'm going to apply L'Hopital's rule. Usually, when you apply L'Hopital's rule, you either put a little L or a little H here to let everyone know you're about to apply the rule. And what we said was L'Hopital's rule allows you to take the derivative of the top and then the derivative of the bottom separately. You don't do quotient rule. It's nothing like that. It's just the derivatives separately. So the derivative of the natural log of something, right, should be 1 over that something. That's the way we always take derivatives of natural logs, right? Derivative natural log of u is 1 over u. So this is going to be 1 over whatever was inside the argument of natural log, which is this. But then the chain rule says, now take the derivative of what's inside of here. I have a sum, so derivative of 1 is 0. The derivative of 5 over x, yep, remember, that's the same as 5x to the negative 1. And when you take derivative, you bring down the negative 1, you subtract 1. So it'd be negative 5x to the negative 2, which is the same as negative 5 over x squared. So that's this part, derivative. Now we're done on top. Now what's the derivative of the bottom? Well, this is x to the negative 1. So negative x to the negative 2, which is the same as negative 1 over x squared. All okay with this? Now, before you go trying to plug infinity in again, something very nice is going to happen. Notice we have the x squared here and the x squared here. And we could essentially take the fraction down here and bring it up and flip it so it becomes x squared over negative 1, and it's gone from there. All right, you flip the fraction up, and then look at the x squareds cancel, and you're just left with negative 5 over negative 1, which is just 5. So this whole thing turns into natural log y equals limit, still have not taken the limit yet. I have that 5 that was left over, and then I still have that 1 plus 5 over x. Now, let me point out something very subtle but important here. We were talking about a sequence, weren't we? And I used the theorem that says, let's go look at the function instead. The reason why we have to do that is because if you had replaced all of these x's and you didn't replace them with x's, you would have left them as n's, then when you got to this step of L'Hopital's rule, when you took the derivative, it wouldn't make any sense. Now, just think about it for a second. If you have a function and you say find the derivative, you're looking at the slope of the tangent line, right? Isn't that what the derivative represents? Yes? And so the way we did derivatives is that we actually took 2 points on a curve and we moved 1 point closer and closer in a limit, and then eventually we converged to some line, right? But the idea was to take a secant line and move one of the points closer, right? That's the idea of the derivative. But if you do not convert this to a function and you have just the dots, right, then you cannot talk about the derivative because it's not defined. If you go to this point and talk about the slope of the tangent line, you need another point that you can slide closer and closer to it. And if these dots are separated and there's big gaps between them, you can't slide towards it. Does that make sense? So derivatives of sequences don't make sense. So we have to look at a continuous function in order to talk about derivative, which is why the theorem is so important. All right? So if on your test or on a quiz or something, you leave everything in terms of n and you never say, I'm going to switch over to a function of x now, technically it's not correct. So you need to, have points taken off for that. All right? All right, now, what happens? X goes to infinity. This term, 5 over x, is going to vanish to 0 now, right? That's going to go away when I take the limit. And all I'm going to be left with is 5 over 1, which is 5. So I know that the natural log of y must be 5. And remember, what we wanted in the very beginning of the problem was we wanted to know what y was, didn't we? Right? So I need to release y from the natural log. To do that, I come in with e on both sides. So I'm going to take e to the natural log y equals e to the 5th power. And that the left side just turns into y, and the right side is e to the 5th power. So that sequence converges, right? It converges to e to the 5th. So what I need to say is something like, therefore, you know, that's my 3 dots is therefore. Therefore, a sub n, which is 1 plus 5 over n to the n, the arrow says converges to e to the 5th. Because the function converged to e to the 5th, and the sequence is defined as the function, just a different domain, the sequence should go to the same exact place. With me? Yeah? Okay. Pardon me? Nope, I would just write this down. Find the limit, this. You would need to know that you need to go to turn it to a function. All right, any questions? All right, let's go to another, what do we have next? A definition. So a definition. Okay, if we write a sub n goes to infinity, we mean for every positive number m, there exists a positive integer capital N such that if little n is greater than capital N, then a sub n, a sub little n, is greater than capital M. Ew. Now, I intentionally wrote this out in a bunch of words because I wanted you to see, I know there's some people in here that are interested in getting into the math field. The way we write something like that as math people, because that's way too much crap to write, right? So what we say is this, that everything in blue there can be written mathematically like this. For every m greater than 0, m element of the integers, there exists capital N greater than 0, n element of the integers, such that if n is greater than capital N, that implies that a sub n is greater than m. I'm just showing you a different way of writing that same exact statement. All right, so an upside down capital A means for every. For every positive m, where m is an integer, actually, you know what, scratch this integer. M doesn't have to be an integer. Scratch that. For every positive number m, there exists as a backwards e like this. There exists a capital N, which is a positive integer, such that if little n is bigger than capital N, a sub n is greater than capital N. What the hell does that mean? We're trying to explain to people what it means to say that a sequence goes to infinity. I mean, for us, we just think about it visually, it goes up, right? The sequence, the dots start going up forever. But here's the visual of this. Okay, so we have a sequence here. Would you agree, just by the look of it, the sequence appears to be going up to infinity? Yes? Okay, the theorem says for every capital M, every positive number, that means somebody pick a positive number. Okay, tell me when to stop. Right there. Okay, right there. So that's a specific example of an M, right? For every M that someone can think of, I can show you that there exists a capital N, that if I go to capital N, it's right about here. If I go to that capital N, then every single term of my sequence past that capital N is bigger than the M that you chose in the beginning. Right? If I pick any number out here, right? This looks like it's what, 32, 4, 6, 8. Yeah, this is like 32. This is the 32nd term of my sequence. So it looks like capital N is 32. If I pick the 33rd or 34th or 35th term of the sequence, they will all be bigger than that capital M, right? So someone says, well, wait a minute, hold on. I think capital M was bigger. So you go and you give me a bigger capital M. Well, I can always find, there's always going to exist a capital N that I can go to, that as soon as I go past that, I'm still bigger than your number. And I can do that for any number you ever give me. If I said for every capital N, there exists an M that's bigger, is that what you're saying? Well, here's the thing. It depends on what we're trying to show. We're trying to show that this sequence goes up forever, right? So what you're trying to do is prove that to someone. So someone comes in and says, no, I don't believe so. I don't think that sequence ever gets past 40, right? And so you say, no, okay, fine. Give me your 40. And now you will be able to now find a place where you're going to go past the 40, right? So you've shown them. Now, I understand what you're saying, but that doesn't gain us anything as far as trying to show that something's going to infinity. To say that, okay, I can pick an N, and then whatever N I pick, there's some M that works like that, yes, but that doesn't help us show that this will hold for every, I'm trying to show that for every M anyone can ever come up with, I can always find somewhere in the sequence where I'm going to be bigger than it. And if that holds for every M, then that means it goes to infinity. Okay, so I'm just trying to get you to see the visual of what this definition is talking about. Okay, next one. This is a result of Ooh. In other words, I'm just saying this is just some consequence that we're not going to get into showing that this is true. I'll show it to you visually, but we're not going to prove it. We'll talk about it. Let's say that we let a sequence be defined to be A sub n is R to the n. Where R is a real number, okay? So our sequence, A sub 1 would be R to the first power, right? So this is what our sequence looks like. R to the first power, then our second term would be what? R squared, the next one R cubed, next one R to the fourth, right? And the nth one would be R to the n, and then you would have more past there, right? Something like that. So the question is, does this sequence converge or not? Well, it's probably going to depend on R, isn't it? I have to tell you what R is. So what does your instinct tell you? Like, what if R was 2? This would be 2 squared, 2 cubed, 2 to the fourth, right? Those are getting bigger and bigger and bigger. That looks like it is going to infinity, right? All right. Do you agree? What if R was 1/2? 1/2, and then what's 1/2 squared? 1/4, then 1/8, and then 1/16. So they're getting smaller, right? They appear to be approaching 0. And in fact, that's going to be our conclusion. But let me show you real quick the geometric. I did all this morning before class. I was just messing around with Mathematica. So here is the sequence with r being 0.5, 1/2. And I think it's obvious, hopefully to you, that this does converge. And it looks like it's converging to what? 0. It's getting smaller and smaller and smaller, right? Now I'm going to control what r is. If I let r get bigger, meaning 0.59, 0.64, right? It's still converging, right? Still converging to 0, but something's happening, right? I'm pulling those points up, but it's still converging to 0. Yes? Something interesting is about to happen. Let's go to 0.99. Is it still converging to 0? Yeah, I just need to go further out into the sequence there. I mean, maybe I need to go further. So it's converging. Okay, there you go. See, now I'm like 500 terms into the sequence. You can see the convergence, right? It's still going to 0. But what's going to happen when I get to 1? They're all 1, right? So now they're all 1, 1, 1, 1, 1, 1, and that is going to converge, right? To what, though, this time? 1. It doesn't converge to 0, it converges to 1. It's 1 identically. Now, what's going to happen when I go past 1? Now they're going to get bigger, right? Because each term of the sequence is getting bigger and bigger and bigger and bigger. So now this thing's going to take off. Now, I'm afraid to show a whole lot more. Let me show 250 terms. Okay, yeah, look, it just takes off, and it's not even on my graph. I can try and zoom out. Yeah, but it's taken off, right? Okay. So go back to 50 term. Okay, and if I keep on going with that r and making it bigger, it's just going to go faster, right? Okay, but what we haven't looked at is what happens when r is negative. So what happens if r is negative? Yeah, because having a negative number, every time we raise it to an odd power, it's going to stay negative, and every time we raise it to an even power, it's going to be positive, right? So what we should get is the same sort of picture we had here where it's diving down, but they should jump back and forth. So let me move this. There we go. Still goes to 0 though, doesn't it? It's going back and forth, but it's getting closer to 0. As long as your r, look at your r here, negative 0.81. What happens though as I keep on going out? Uh-oh. Uh-oh. It's still going to 0, right? But those are spreading apart. And then what's going to happen here when I go to negative 1? It's going to be 1, negative 1, 1, negative 1, 1, negative 1, back and forth. Does that converge? Does this sequence converge? No. It goes back and forth. So it diverges, right? Remember, sequence either converges or diverges. So it looks like there's a couple of things we can put together here. And let me try and summarize it all in one nice little thing. Here's what we have. If a sub n is r to the n, which looks like this, then the limit as n goes to infinity of r to the n will equal one of three things. It'll be 0 if the r value is between negative 1 and 1, right? We saw that if our r value was smaller than 1 or bigger than negative 1, right, then, or between those two values, then we saw that it would eventually go to 0. Now, what happens if, how do I get 1 to be my limit? If r was 1, right? If r is exactly 1. And then what I'll say here is diverges if, I'll use some computer language, else. Right? What does that mean? If it's anything else other than these conditions, it diverges. So if r is negative 1, you're not here. If r is negative 1, you're not here. So that means you have to be here. That means it diverges. Now, we said that if r was 2, it took off to infinity, right? Right? It took off to infinity. Just keep in mind that the only way you can say that a sequence converges is if it goes to a number. If it goes to infinity, it's still divergent. It just diverges to infinity. All right? So divergence and infinity kind of mean the same thing, but divergence does not mean necessarily it has to be infinity, right? That up and down, back and forth, -1, 1, -1, 1, that's divergent, but it's not infinite. It's not going to infinity. Understand? So infinity implies divergence. Divergence does not imply infinity as a limit. Okay, so we will want to keep this in mind. Anytime we have a sequence that involves something to the n, we'll look at that something. We'll see what's the value of that base, and we'll use these results to draw some conclusion. Give you an example right now. Find the limit as n goes to infinity of 3 to the n plus 1 over 5 to the n. Yeah, over 5 to the n. So let's just look real quick, like we did back in calculus. What's happening up here? What's happening down here? So 3 raised to the infinity . 3 raised to the infinity is getting infinite, right? Adding 1 to it, still infinite. So we have infinity up here. On the bottom we have infinity also. Infinity over infinity is usually L'Hopital, right? However, I would have to convert it into a function of x first, right? And do all that. But maybe there's a way I can do this without L'Hopital. Okay, maybe there is. Let's take a look at something here. Do you agree that this is the same as the limit n goes to infinity of 3 to the n times 3 over 5 to the n plus 1 over 5 to the n? Whoa, what happened there? What did I do? I split it. Since I have 2 terms up here and 1 down here, I put this on top of this and this on top of this, right? Do you agree? And separate them with the plus sign. Now, I rewrote 3 to the n plus 1 as 3 to the n times 3. Do you agree that that's the same? We're going to do that a lot, so get used to it. This is the same, right, as this? Now, the reason why I did that is because I want you to notice that these 2 factors are both raised to the n power, right? So there's a property of exponents that says I can write this. Limit n goes to infinity. I can rewrite that 3 to the n over 5 to the n as 3 over 5 to the what? N. Then I still have sitting next to that what? 3. Everybody agree with this? Okay, so this is this, and then over there, check this out. I think you can kind of tell what's going to happen to this one, right? This is 1 over infinity. It's going to go 1 over infinity. But could I write it like this? 1/5 to the n? Because if you take 1 and you raise it to the n, you get 1. 5 to the n, you get 5 to the n. So this is the same as this, isn't it? Questions? We're not, no, what's that? If this, it would be 1, we'd have 1 to the infinity, but I'm so glad you're bringing this up. Okay, here's the question, and this is, I'll never forget, I had a student many years ago who took Cal 2 with me and then was taking some other class somewhere else and called me up like 2 years later and was like, man, you told me that 1 to the infinity was like something, and got all mad, and obviously I did not make the connection for the student. So let me make sure that I'm making this connection here. Where were we? This one? Okay, 1 to the infinity, we had to do all this work, right? But the key here, I said I did this in red for a reason, Because I'm not saying that this base is 1, am I? I'm saying that this base here is close to 1, right? There's a difference between something being 1 and being close to 1. When I plug in values for n, this number right here gets infinitesimally small, but I'm still adding 1 to it, so that's a number a little bigger than 1. So this base is approaching 1, the exponent is approaching infinity. Compare that to this. This right here, this number is 1. There's no messing around with that. That is 1, right? This is 1. And so if I take 1 and I raise it to any power, I'm going to get 1 still. See the difference between the two? It's identically 1 versus approaching 1. And so that's why I can rewrite this. I can put this n in here, right there. 1 to the n is still going to be 1. And then I rewrite it like this. We okay with that then? Okay. Is that what you were referring to? Okay. All right. So now, why I did this is just so I could recognize these two things are separate problems, but this is an r to the n and an r to the n, isn't it? The r we have here is 3/5. 3/5 is less than 1, right? This is 1/5, that's less than 1. Because of the note we just had, I know that those two sequences individually go to 0, don't they? So I know that this guy, that sequence is going to 0. Then times 3 is still going to be 0. Plus this sequence right here is going to go to 0. So I can tell you that this limit goes to 0. Part of the challenge is converting the sequence into something that you can manage and something you know about. All right, let's keep going. Another definition. A sub n is said to be increasing if a sub n is less than a sub n plus 1 for all n. I'm using that upside down capital A for all to mean for all now. You all okay with that? To say it's increasing means it's going up, right? That makes sense? It's going up. So this is saying that, look, the nth term of the sequence is smaller than the n plus 1 term, the one right next to it. And that always holds for every n. So I could be saying that the first one is less than the second one, right? But that one has to be less than the third one, which has to be less than the fourth one, and so on and so forth. So if they keep getting bigger as you go. That's called an increasing sequence. Decreasing would be the same thing. Swap the inequality over, right? Flip it. So a sub n is said to be decreasing if a sub n is bigger than a sub n plus 1 for all n. So that means the first one is bigger than the second one, is bigger than the third one, is bigger than the fourth one, and they keep getting smaller and smaller. In either case, a sub n is called monotonic. So if I tell you, hey, I've got this sequence and it's monotonic, does that tell you it's increasing? No. If I tell you it's monotonic, does that tell you it's decreasing? No. It tells you it's one or the other, though, right? It's one of those. So monotonic is a little more general to say something is monotonic. To say that it is increasing means it is monotonic and it gets bigger as you go. So sometimes we say, instead of increasing, we say monotonic increasing, but it's kind of redundant to say monotonic increasing because monotonic already means it's either increasing or decreasing. And if it's increasing, it's already does that make sense? I mean, so monotonic just gives you a certain type of sequence. It's either increasing or decreasing. Okay, got that? That's just definition there. Questions? Okay, another definition. A sub n is said to be bounded above if, now here I'm going to use math writing here. What is this? If there exists a capital M such that A sub n is less than capital M for all n. To say that a sequence is bounded above, I mean, does it make sense bounded above what that would represent? You have an upper bound, you have like a ceiling, right? You have some number that your function never gets past, your sequence never gets past that point. You have an upper bound, yes? And a lower bound or bounded below would mean that you have some number that your function is never less than. I say function, I mean sequence. Sequence is a function. I should be saying sequence, though. So the other definition here is that A sub n is said to be bounded below if there exists a little m such that A sub n is greater than little m for all n. In either case, A sub n is said to be what? If it's bounded above or bounded below, either way, we'll consider the sequence to be bounded. Okay? So if I tell you a sequence is bounded, I'm not telling you if it's bounded above or below, right? I'm just telling you it's bounded. If I say bounded above, then you know that there's some top it can never get past, and if it's bounded below, there's some bottom it can never get past. I put the picture together because it was really easy to change the code to show you this, but here we go. Here's a sequence. That might be too many points. Let me bring this back. Okay, here's a sequence, right? The sequence appears to be approaching 0.5. All right? Yes? Is it bounded above? Yes. Is it, right? Is there a number that it never gets past? Here's any of these, right? One would be an upper bound, right? 2 would be an upper bound. As long as there's some number it never gets past, it's bounded above. Now it's not. We're not trying to figure out what this least upper bound would be. That's something you do later. But at least here we can say it never gets past a certain value, 1. And is this one bounded below? Is there a number that the sequence never gets below? Yes. So bounded above, bounded below. This one is bounded above and below, isn't it? Not every sequence would be bounded above and below. By the looks of that sequence, is it monotonic? Just from the look of it. It's not continuously increasing. This point is smaller than this one, right? Is this point is smaller than this one. Is this one smaller than that one? Whoa. Is this one smaller than that one? This one smaller than that one? That one, that one, that one, that one. Yes or no? I mean, we can sit here and debate it, couldn't we? So let me show you. I'm actually going to take this sequence. I'm going to change it a little bit. I'm going to change it to, instead of this, I think I'll make it 1 minus 1 over n instead. It just looks a little different, okay? I'd like to take that sequence, 1 minus 1 over n. I want to show that it's bounded, and I want to show it's monotonic. All right? I'm going to show that to you. Because you can do it by looking, but sometimes you can't just look. You have to show it a different way. So let me show you the method. As an example here, show a sub n equals 1 minus 1 over n is bounded above and below. I want us to show that. And then is a sub n monotonic? All right, so what does it mean to show that it's bounded above? That there's some number, right, that it never gets bigger than? So let's act like we didn't have that picture, right? Let's act like we didn't have the picture. Then what we might want to do is actually list out the first few terms of this sequence, which would be what? What's the first term in this sequence? 0 first, right? Then, so I plugged in 1 right here, right? Got 1 minus 1 is 0. Now plug in 2, 1 minus a half. Okay, next one would be 1 minus a third, 1 minus a fourth, and so on and so forth. I believe that we would all look at that, and we would all say this appears to not ever get bigger than what number? It never appears to get bigger than 1, does it? I mean, you can even look at this right here and say, oh, well, look, I'm having the number 1, I'm always subtracting something from it, right? So it's got to be smaller than 1. But again, later on, may not be so easy to see that. So what's the method? You have to make some sort of guess at it. I think it's always going to be, let's say, this thing will always be less than 1, right? So what I'm going to do is I'm going to ask myself a question. Is 1 minus 1 over n less than 1? This is a question I'm asking. If it is, then I'm going to show it's bounded above, right? So this is an inequality. I'm going to subtract 1 from both sides. My next statement is negative 1 over n is less than 0. Do you agree with this? Are you ready to draw a conclusion that yes, this is true? Yes? Okay, convince me. Why is this always true? This is always a negative number? What if n is a negative number? If this was a negative, then it would be positive, right? But what? But why can't n be negative? It can't, right? We always started at 1, right? We didn't always start, but I didn't say it was somewhere else, right? Since I didn't say where it started, we assumed it was 1. So I can conclude from that this is true, that the left side is always negative. Now I could also do this. I could multiply both sides by n, right? But when you multiply both sides of an inequality by a number, you have to be careful, because if you multiply by a negative number, what happens? It flips, right? But again, I know n is not negative, so I'm going to multiply both sides by n and not flip the inequality. And if I do that, the n's on the left cancel. I get negative 1 is less than what? 0. Is that true? Yes. That I'm pretty damn sure about. Now, I will make a statement here. Remember, n is greater than 0. That's why I could do this. That's why I didn't have to flip the inequality. Make sense? So I've shown it's bounded above. Therefore, A sub n is bounded above. Now, what was our guess for bounded below? 0. How about -1? I want to play it a little safe here. How about -1? Do you agree? I mean, those things are never negative. So let me go with -1. I just have to pick anything. So now my next thing is 1 minus 1 over n, what? -1, how? What's the relationship I'm trying to show here? Is it greater than -1, right? Is it greater? So what I'm going to do is work with this inequality. I'm going to add 1 to both sides, and I'm going to add 1 over n to both sides. So by adding 1 here and adding 1 here, I get a 2. By adding 1 over n here and 1 over n here, I don't have to worry about flipping inequalities because I'm adding. I get this. Is that true? Well, maybe you're convinced with that, but I will multiply both sides by n here, again, because I can and not have to worry about flipping. Is 2n greater than 1 for n bigger than 0? Is that true? Yes, because not only is n bigger than 0, we said n had to start where? At 1, so you would get what here? Here's something else you could do if you really want to convince yourself. How about divide both sides by 2? Is that true? Is n greater than 1/2? Yes, because we're starting at 1, right? I like that. That convinces me pretty dead on. N is greater than 1/2? Yes, because I'm saying it starts at 1 and goes on. So I'm convinced that that inequality holds. Therefore, A sub n is bounded below. So I've shown it's bounded, right, above and below. Not every sequence is bounded above and below. Y'all hear me? Not every sequence is bounded above and below. I need to now show what? Or it asks me, is it monotonic? Well, again, I need to look at this and convince myself whether or not I think it is. So it starts at 0, gets bigger 1/2, bigger 2/3, bigger 3/4, bigger 4/5. Looks like they're getting bigger, right? Bigger and bigger. So I'm guessing that maybe this is increasing, right? Is it increasing? So check this out. My guess is I think A sub n is increasing. Okay. Again, I'm kind of thinking that looks like what's happening. Now, to be increasing means that this has to be true, doesn't it? That has to be true to say something is increasing. The nth one is smaller than the next one, the n plus 1. So this is where we have to actually do a little algebra. What is A sub n? What is it? It's 1 minus 1 over n, isn't it? That's the definition of the sequence I'm talking about. I need to show you and convince you that that's less than 1 minus 1 over what? N plus 1. So does everyone see this is A sub n? This is what happens when we plug n into the sequence. Does everyone see that this is what happens when we plug n plus 1 into the sequence? See the difference? I need to see, yes? Okay, I need to show that that inequality is true for all n greater than 0, n being an integer. How about we subtract 1 from both sides? Yes? So I have -1 over n is less than -1 over n plus 1. I don't like the negative signs. So I'm going to move the one that's negative on the right to the left by adding it and move the one that's on the left to the right by adding it. Right? So just swap the sides. So it becomes 1 over n plus 1. Do not flip the inequality, right? I did not multiply. I added or subtracted, whichever way you want to look at it. So this should still hold, right? Now what I'll do is I'll do kind of like what people like to call cross multiplication. I don't like to call cross multiplication. All you're doing is clearing your fractions out. So you're going to multiply both sides of this equation or inequality by n plus 1, n plus 1. So on the left, now I do that, do I have to worry about flipping the inequality here? No, because n's not negative, right? So I can be guaranteed that my inequality is going to hold here. So let's go ahead and let's cancel those, and then we'll cancel the n's here. And what I get is n is less than what? N plus 1. Are you pretty convinced yet that this is going to hold up? Yeah. N should be less than n plus 1, but you could even subtract n on both sides, and you get what? 0 is less than 1? And that is always true. Therefore, our assumption that a sub n was less than a sub n plus 1, hold on, let's wait. Go ahead. We'll let you go. Apparently you don't like it. Have fun. Have a good day off. I promised her I'd give her a hard time. She told me she was going to leave early, so I promised her I'd give her a hard time. Are you following the logic here of this? All right. You cannot, if I ask you on a test or something to show that something is monotonic, you can't just be like, yeah, because that's getting smaller. I mean, you can't just look at the sequence. That's not the point. The point is the algebra in here and making sure you understand the logic behind it. All right, so we have what? Therefore, this a sub n is increasing. We could say monotonic increasing, but that's good enough. Okay, we're going to move on. Yes? It can't be both. That's right. Good question. You can't be both increasing and decreasing. Well, increasing means that each successive term of the sequence is bigger than the one before it. Decreasing means each successive term is smaller, or yeah, below it, if you look at it graphically. So yeah, I mean, you could say it's not like going all of a sudden jumps up. So we can't have that one that we had that was -1, right? That's not increasing, that's not decreasing. But that would be divergent, yeah. So now the question becomes, well, it's a theorem, so it's not really a question, but I think when I write the theorem down, you'll hopefully be convinced that this theorem makes sense. Every bounded monotonic sequence, what? What do you think? Every bounded monotonic sequence must increase or decrease, yes. Must converge. Must converge. Let me try and give it to you graphically. All right? Let's say that I have a sequence and it's bounded, right? Increasing, but bounded. Then the fact that I can't go any higher, but the fact that I have to keep getting closer would force me to converge to something. All right, it's a little bit harder to show this than just that picture, which is why it's a theorem, because you have to prove all these different cases. But we're just going to take it for what it is, the theorem. This is a good way to show something converges. You just figure out if it's bounded, and then you figure out if it's monotonic or not. So you do the two things I just did. You figure out if there's some number you know it's not ever bigger than. You show that that's true. You show that it's either increasing or decreasing. The conclusion of that is that it must converge. What this theorem does not give you is what it converges to, right? It just tells you it converges or diverges. And that is a good thing because, well, it doesn't tell you if it diverges. It just tells you if it converges. That's actually a good thing because where we're headed later is we aren't necessarily going to be talking about always being able to get what something converges to. It's just being able to determine whether or not it converges or diverges, one or the other. All right. I had an example here, but I think that that's okay. I won't do that one because I gave you another one. That's fine. All right, next one. This is an example. This is a pretty interesting example. Find the limit of this sequence. Find the limit of this sequence. The square root of 2, the square root of 2 times the square root of 2, the square root of 2 times the square root of 2 times the square root of 2, times the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2, dot, dot, dot. You get the idea? Every time you go in, there's another square root of 2 next to the 2, and then you just keep doing that. I want to know if this converges or diverges. Or actually, I don't want to know that. It does converge. I want you to tell me what it converges to. This is a weird problem, which is why I'm giving it to you, because we haven't even looked at anything like this. Let me let you think about that for a minute. How about that? Let you kind of simmer with that, maybe bounce some ideas off each other. Make this an in-class quiz? No. No. See what you can do. You got to try something, okay? My recommendation to you would be this. Try and come up with a formula for it. A sub n. Right? I've given you the sequence. Like, if I gave you 2, 4, 6, 8, 10, you would say A sub n is 2n. Well, I gave you this, and you try and come up with some sequence definition for it. I'm going to take a quick little break. Just ponder life. What's that? Well, if you're going to write a formula for this, then yes, n would go to infinity once you have your formula. Does this go to infinity, though? Are these getting bigger and bigger? They're actually, I think they're getting smaller. But, okay, so here, check this out. I'm going to rewrite the first term here. This is 2 to the 1/2, isn't it? Okay, the next one is, let's see, the square root of the whole thing, right? And then inside, what's inside of that first square root there? 2 times what? 2 to the 1/2 again, yes? I could write it that way. And then the next one would be square root. Inside that I have 2 times, but then I have another square root, don't I? And then I have inside that 2 and then 2 to the 1/2 again. Do y'all follow this? And then the last one I'm not even going to write. Okay, so here's what I've got. I got 2 to the 1/2 here. Now here, because this is an exponent, and because I have multiplication here, I can apply the exponent to each of these, right? Which means this will become 2 to the 1/2 times 2 to what power? What happens when I do this and this? You multiply the powers. So 1/4. Okay. So this piece right here, right? This whole thing is actually this piece right here, isn't it? Like that is the same as this. And that turned into this. Yeah? So my next one would be 2 times, now the yellow part turns into 2 to the 1/2 times 2 to the 1/4, but then all of that to the 1/2. Are you following me? This is all just using properties of exponents. What is that first one in yellow there? What's 2 to the 1/2 times 2 to the 1/4? 2 to the 3/4, isn't it? Yes? 2 to the 3/4. So this is 2 to the 1/2. The next one is 2 to the 3/4. The next one is, let's see, this is 1 plus a half, that's 3/2, plus a 1/4, which is 7/2. And then to the 1/2 means you multiply, you get what? 7/8. 2 to the 7/8. And then the next one, which we didn't do, would be 2 to the 15/16. Now, what stays the same all the time in every one of these? The 2, right? So I'm thinking that my a sub n is going to be 2 raised to this power. Now look at this power. Remember how I said when we look at sequences, when you look at fractions, you look at like top and bottom separately? I'm actually going to look at the bottom first because I recognize 2, 4, 8, 16, those are all powers of 2, right? This 2 to the first power, 2 squared, 2 to the third, 2 to the fourth. So I'm thinking that this fraction here is 2 to the n there. I don't like writing my fraction like that. I prefer to write it like this. 2 to the n is on the bottom. Is that all right? That's what this is. And then what about the 1 and then the 3 and then the 7 and the 15? Isn't the 1 just 1 less than the 2 and the 3 just 1 less than the 4 and the 7 just 1 less than the 8? And so isn't it just the 2 to the n that we had on the bottom just take away 1? Ooh, wow, this is weird, huh? That is the sequence right there. So I'll write it down below. A sub n is 2 raised to the 2 to the n minus 1 over 2 to the n. And I want to know now what happens as n goes to infinity. And look at this right here. That's infinity on top and infinity on the bottom, right? Indeterminate form. I could try L'Hopital's rule and all that, convert it to a function of x, but 2 terms on top, 1 term on the bottom means I can split it in 2, can't I? So this just turns into 2 raised to the, what's the 2n over 2 to the n over 2 to the n is 1, minus, what's 1 over 2 to the n? Just 1 over 2 to the n. Yeah? Now, take the limit as n goes to infinity of 2 to the 1 minus 1 over 2 to the n where does that go? So 1 over 2 to the n goes to 0, right? 1 minus 0 goes to 1. So 2 to the 1 is just 2. This sequence converges to 2. Wow. Right? I mean, now that you see it, I hope that the moral of the story here is just that, you have to be prepared to work with exponents, be comfortable with, radicals converting over. There's nothing off limits when it comes to this. All right, I'm going to work some problems, do more examples here. Let's see, how about something like this? For all of these problems, I want us to find the limit as n goes to infinity of a sub n. I just don't want to have to write that over and over and over. So what about this sequence? So tell me where this goes is I take the limit as n goes to infinity. Where does the numerator go? Goes to infinity. Denominator? Infinity also. So infinity over infinity, you can try L'Hopital's rule, but does anybody feel like taking the derivative of the bottom? Not really, right? So whenever you have polynomials like this, what we usually try and do is wipe out the highest power that we see in the denominator. So like I want to wipe out an n to the 6th. That means I want to divide this by n to the 6th. So the way we do this is, I better write the limit down. Limit n goes to infinity, n cubed over square root n to the 6th plus n plus 1. There's all different ways that instructors approach this. Here's the way that I do it, okay? I want to wipe out an n to the 6th. So what I'm going to do is on the outside of this, I'm going to multiply by 1 over n cubed. And whatever I do on the bottom, I have to do on the top. So I'm multiplying by a 1, basically. But why do I use 1 over n cubed out here? On the bottom, correct. So remember, if you take something out of a square root, right, then you're taking the square root of it as it comes out. If you try and force something back into a root, it gets squared on its way in. So if I take 1 over n cubed and I push it into the root, it's going to become 1 over n to the 6th, which is what I want because it'll kill off that n to the 6th. So pass everything through. On the top, what happens? You just get 1. On the bottom, we still have the square root, but now we've pushed the 1 over n cubed in. When it goes in, I'll do it in red here. When it goes in, it sits right there next to all that, and it turns into a 1 over n to the 6th, right, when it goes in. And then pass 1 over n to the 6th through to each of those. And what would you get? 1 plus 1 over n to the 5th plus 1 over n to the 6th. Do y'all see that? 1 over n to the 6th times n to the 6th cancels, you get to 1. N over n to the 6th is 1 over n to the 5th. Then 1 over n to the 6th is 1 over n to the 6th. And why is this all good now? Yeah, let n go to infinity, right? This goes away, that goes away. And what you're left with is what? 1 over the root of 1, which is just 1. So this sequence converges to 1. Standard trick here, standard approach to a limit like this. How many of you have seen that? Yeah? A couple? All right, you got a lot of work to do. Okay, how about this one? find the limit as n goes to infinity of sine of pi n over n plus 1. So what's happening here? N goes to infinity, you get infinity here, infinity over infinity is, I don't know, depends, right? So now I have to do something here. Kind of the same thing we just did, right? You could look at this and say, hey, look, I can divide both the top and bottom by what? By n, or multiply by 1 over n, right? And kill off that n. Now, could you do this? Could you real quick on the side go, I'm just going to look at pi x over x plus 1. Could I do that and just focus my attention on what's going on in here? Turn it into a function. That seem fair to you? And then it's still infinity over infinity, right? And I can use what now? L'Hopital, right? Change that f of x to a limit. Let's just go straight to this. Limit x goes to infinity. So this is like a little scratch work I'm doing on the side for this problem. I'm going to apply now L'Hopital's rule, which means derivative of the top, which would be what? Pi, derivative of the bottom, which would be 1. So that limit is just pi. And since this is happening for the function defined on all real numbers, the sequence must follow it. And so I know that the inside of this is going to go to pi. So now what you're really saying is what's sine of pi? Sine of pi is 0. That's right. There's actually there's a theorem in the book. I didn't show it to you, but I wanted to explain that to you in an example. Is that if your function is a continuous function, like sine is continuous, then you can pass the limit through it and go inside and take care of what you need to in here, and then just whatever that answer is, plug it in. That's right. You could do the same way. If this was e to this, your answer would be e to the pi. Yeah? Okay. All right, let's try another one. How about if we have limit n goes to infinity, cosine n squared over square root of n. So what's happening here? Up top, n goes to infinity. What's cosine of infinity? So what does the cosine function do as you go out to infinity? It's going to oscillate, right? But this is a sequence, so it's like dots, and they're jumping back and forth, right? Yes? And then what about the denominator? Going to infinity? So, but the numerator, that limit doesn't exist, right? It's not going to infinity. It's not going to, it's just jumping back and forth. So you can't say here infinity over infinity. You can't say 0 over 0. You can say, I don't know, over infinity, right? It is bounded over infinity, though. You have something that's bounded on top between -1 and 1 and something that's getting huge on the bottom. So, but the way I'm going to do this is I'm going to use Squeeze Theorem real quick. I know this is true. Do you agree with that? Cosine n squared has to be between -1 and 1. Because that's what, I mean, that cosine function is always bounded between -1 and 1. Then what I'm going to do is I'm going to try and make this guy appear. So I'm going to divide this through by the square root of n, and that means I have to divide all of the pieces of this inequality by square root of n. Do I need to worry about flipping inequalities here? No, because square root of n is always a positive number. And now what I do is I take the limit. And what I'm hoping for is that the two n's are going to go to the same place and squeeze this one in between, which is what happens. If I go and let n go to infinity, this goes to 0. This one goes to 0, right? Because you have fixed over infinity, fixed over infinity. Those both go to 0, which forces the one in the middle to also go to 0. So your answer here is 0. Now on a test, if you said bounded over infinity, I'd be happy. Okay? Okay, another one. Find the limit. N goes to infinity. Natural log n squared minus 1 minus natural log of n cubed minus 1. What you think? Yeah, this is infinity, right? Natural log of infinity is infinity. Infinity, natural log of infinity is infinity. This is infinity minus infinity, which is an indeterminate form. We cannot tell what's happening here. But you can apply properties of logs that says if you have log of something minus log of something else, you can turn it into a single log, and you convert the subtraction into what? Division. So this turns into n squared minus 1 over n cubed minus 1. And this is infinity over infinity in here, isn't it? So you could divide through by 1 over n cubed on the top and bottom, or you could do a L'Hopital rule on the side here, converting it, or you might even see this. Anyone see those factor? Well, maybe that doesn't help so much. N plus 1 times n minus 1, difference of squares on top. And on the bottom, that's a difference of cubes, so it's n minus 1, n squared plus n plus 1. I just noticed that. I mean, I don't know if that's really going to help. I'm still going to get infinity over infinity, right? But I mean, you can almost just see right now that if you do L'Hopital's rule one time on this, what are you going to get on top? A 1, and on the bottom you would get 2n plus 1 or 2x plus 1, and that would give you 1 over infinity, which would go to 0. So this thing is approaching natural log of 0, right? I'm not going to show the work for this, but this is approaching 0. What's natural log of 0? I keep threatening my Cal 1 students that I'm going to give them a quiz on the natural log function. Natural log looks like this, right? Natural log of 0 is undefined. However, this is a limit. This is getting closer to 0. So what's happening in the natural log as we get closer to 0? It's going to negative infinity, which means that this sequence diverges. This is a divergent sequence. Therefore, divergence. You can be monotonic and diverge. Monotonic just means that you're going always increasing, always decreasing, but you can be monotonic and diverge. Bounded, if you're bounded, you can't go to infinity, right? If you're bounded above, you can't go to infinity. All right, let me see here. I haven't given you any alternating sequences, but I think I'll let you handle those. Man, there was one, but I can't find it now. Where the heck is it? Well, I remember it, so let me just see if we can look at it, okay, and see what you think of this sequence. N factorial over n to the n. Now let me point something out to you here. You can never switch this over to f of x equals x factorial over x to the x, because x factorial is not defined for anything other than positive integers, or 0, 1, 2, 3, right? Factorial is not defined. So this is an example of a sequence where you cannot save yourself by going here and then trying to use L'Hopital's rule. It's not going to happen. All right? Now let's talk about what's happening to this. As n gets bigger, this n factorial should get huge, shouldn't it? And then n to the n is like infinity to the infinity, which is getting huge also. I guess the question is, which one gets bigger faster? The bottom, you think? Well, let's take a look real quick. Would you agree that a sub n is n times n minus 1 times n minus 2 times n minus 3, all the way till you get down to what? 1, right? That's what the definition of n factorial was. What is n to the n? What's n to the n? That would be n times n times n times n, and you keep doing this all the way till you get down to the last one, which would still be n, right? And how many of them would you have? N of them, right? That's what n to the n means, repeated multiplication. It's n n's. And notice with the n factorial, we have, like if you had 4 factorial, it would be 4 times 3 times 2 times 1, wouldn't it? So how many factors do you have here? For 4 factorial, you have 1, 2, 3, 4 factors, right? For n factorial, how many factors do you have here? 1, 2, 3, 4, n of them, right? So for every n here, I have this matching exactly, right? Do y'all follow this? Okay, do you see, first of all, that these cancel? Yes? What can you tell me about this right here, everything over here? If this is n minus 1, right, and this is n minus 2 and this is n, would you agree each of those is less than 1? Yes? All of those are less than 1? You all okay with that? So each one of these is smaller than 1, smaller than 1, smaller than 1. What I'm going to try and do is use the squeeze theorem here. I'm going to now show you that this a sub n, which I have written, I don't want to rewrite it all again, but a sub n is this whole thing, must be bigger than 0. Do you agree with that? These are positive numbers. It's got to be a positive number, right? And I'll even put equals 0, doesn't change it. And I'm going to say that that's less than 1 over n. Why is it less than 1 over n? Well, 1 over n I didn't circle here, right? On purpose. If each one of these numbers is smaller than 1, then when you multiply them together, they're smaller than 1, right? So this number right here, all of them together, is less than 1 times this. So a sub n should be less than 1 times 1 over n. Did I lose you? And then if I apply Squeeze Theorem, this side goes to 0 without doing any limit. Where does this go as n goes to infinity? 0, which means that this must go to 0. So by the Squeeze Theorem, this goes to 0. This goes to 0. N to the n is one of the fastest growing functions that you can possibly have. Even x to the x. That function grows extremely quick. It's hard to come up with anything that grows faster than that. Okay, I'm about out of time. Let me give you your homework assignment. We are going to be officially done with 8.1, all right? It's today, Tuesday? Oh, good. Thursday we can do next. Please do as much of this homework as you can before next class, because you'll need it as we move forward. I had already assigned some stuff, hadn't I? 5 through 8, right? So now you can look at 9 through 32, 37 through 40. It's a lot of problems there. My recommendation, as always, is work through the odds first and then go back and try and look at your evens. All of these problems, you're trying to find the limit as n goes to infinity, except for these. I think 37 through 40, determine if it's increasing, decreasing, is it bounded? So that's what these last ones are.